Alright, so you've been watching the history of geometry and architecture, and now it's time to talk about some of the mathematical theories and proofs behind this. It's almost impossible to talk about geometry or how geometry relates to architecture without talking about Pythagoras and his Pythagorean theorem. A little bit of history behind him is that, Pythagoras is credited with coming up with the a squared plus b squared equals c squared and the proofs. There's no actual written evidence they came up with the proofs of these. But the Pythagorean theorem is credited to him. Now, we do know that the Babylonians, for instance, knew about this concept well before Pythagoras, but the cuneiform documents that we have on their knowledge of it have not been fully transcribed and have not been fully published, so we don't really know. So the Pythagorean theorem, as of right now, is still credited to Pythagoras. Alright, so let's get started. What does the Pythagorean theorem tell us about geometry, about architecture, about the real world? Well, it tells us that we can find the length of the hypotenuse, or the c side, without knowing the actual length. Alright, we have the a side, the b side, and from that we can figure out the c side because his theory says a squared plus b squared equals c squared. So if we know that side A is 5 and side B is 12, we can find out the length of this side, side C, which is the hypotenuse. Now how do we figure that out? Well, we plug it into the actual theory. So we would go, and this thing's going to mess up on me again. And we're going to go side A. Alright, so side A is 5 squared. Side B, and that's plus, side B is 12 squared, and that equals c squared. Now this turns into a bit of an algebra problem here because it's sort of like a linear equation if you're familiar with those. So we want to isolate c, so we have to do the square root of c to get rid of the square. Now whatever we do to one side, we have to do to the other side, so this becomes the square root of 5 squared and 12 squared. From here we just do the math. 5 squared is 25. And I apologize for my writing on this screen. It's kind of hard with a mouse. And the 12 squared is 144. Alright, and this equals c because we've gotten rid of the squared. And so this is still squared. So this equals 169 squared, and that equals c. 169 squared is 13, and that equals c. So according to the Pythagorean theorem, the length of side c is 13. But how do we know that's true? That is the age-old question that has dogged geometrists forever. How do we know that the Pythagorean theorem is correct? Well, that's where the historical geometric proofs come in, and we're going to get into those next. Alright, so we have figured out that, a squared plus b squared equals c squared is the Pythagorean theorem. We figured out how to use it. I showed you just a few minutes ago how to plug in the numbers and get the answer. We figured out that side c right here is 13. Now the question becomes, how do we prove this? Alright, so now we're going to do a geometric proof. And this is going to be a geometric proof of the Pythagorean theorem. Now, I've already taken the liberty of copy and pasting all of these triangles because when I was trying to actually do it while talking, it turned into just a complete nightmare and a complete mess. But I assure you that this triangle right here is the same triangle that is right here. And this triangle right here is the same one that's right here, it's right here, it's right here. So we can take we know for a fact that all of these side A's are the exact same length, all of these side B's are the exact same length, and all of these angles right here are right angles. So we know for a fact that this is a square. This is a large square. And the inside is also a square, we think, but we have to prove it. So the way we're going to prove this is because if this is a square and all these right angles, all these are right angles, and then all of these lengths are side C, then that proves it's a square. That proves that side C, that proves our hypotenuse's length. So let's get started. Alright, so you may or may not know that the degrees of a triangle, and when you add up all the sides, is 180. So, if this is angle X, and this is angle Y, and then this is a 90-degree angle, we end up with X plus Y plus 90 equals 180. So it's a linear equation. We just subtract 90 from both sides, and you end up with X plus Y equals 90. So that tells us when you add up angles X and Y, you get 90. Now, why is this important? This is going to help us prove that all of these angles in this square in the center are right angles. So if we have X, Y, right here is X, right here is Y, and right here is Z. So you may or may not also know that you have a line, and you have three angles on it. A line is also 180. So it doesn't really matter what these angles are individually. This angle plus this angle plus this angle are going to add up to 180. So what do we have here? We have a line with X, Y, Z. We already know that X and Y are 90 when you add them together, which leaves 180. So 180 minus 90 equals Z equals 90. That tells us that every single angle in this square is a right angle, and every single line is straight, and it's all C. You have C, 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 and right angles. That tells us that what the resulting shape in the center is an exact square. Alright, so we have just figured out that the inside resulting object is a square. We figured out that all the sides are the same. Every side is C and C and C and C, and all of these are right angles. We have proven that. Alright, so it is a square in the center. Now we want to think about how do we get the area of that square. Now the easy way to do it is just C squared, right? I mean, that's the area of this inside square, but we want to figure out let's do it a little bit harder. We want to figure out the area of the bigger square minus the inside square. So to do that, the area of these bigger squares is this, every side is AB, 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 AB. So the way you would write that would be A plus B times A plus B. And I apologize for the writing as well. Alright, so that's the area of the bigger circle. But we want to get the area of the bigger square minus the inside square. So let's minus, and we know that the area of a triangle, or we should know, is 1/2 A times B. So it's going to be length times height, or base times height rather. So it's going to be 1/2 base times height, and so we have 1, 2, 3, 4 triangles. So that is 4 triangles at 1/2 times base times height. Alright, so now we have to simplify this whole equation. This is a little bit of algebra. It's not too hard. We're going to have AA, so that's A squared. Oh, that's a terrible looking A. That's too bad for even me to live with. So there's A squared. Then we're going to end up with 2AB, 2AB. Alright, these are all pluses, plus, plus. And then we end up with B times B is B squared, minus, and this is simplified down to 2AB. Now, right off the bat, we're able to cancel these out. That's 2ab, 2ab. There's no point in a minus 2ab plus 2ab. That's just, they know one another. So what we end up with is a squared plus b squared. So up here we have c squared equals a squared plus b squared. And guess what? What does that look like? So c squared equals a squared plus b squared. We've proven it with this geometric proof. And what was our original formula? A squared plus b squared equals c squared. It's just a backwards way of writing the Pythagorean theorem. So there you go. We have proven that the Pythagorean theorem works. That's the geometric proof. Now we're going to continue on with our history of geometry and our history of architecture and how it relates to the real world. But now you know how to actually do the geometric work that we're going over. All right.